today we thought it would be really fun as a way to wind down the season of RLAI Tea Time Talks by getting off campus and coming into what's been a really special space for the tech community here in Edmonton for over a decade now here at Startup Edmonton. So big shout out to our hosts for lending us this space to celebrate. They're actually going to be moving out of this space into an exciting new one down the street. So we're going to burn it down tonight. No, I'm just kidding. But we are going to have a really incredible talk from a man who probably needs no introduction in this room, but I'm going to hand it over to Dr. Richard Sutton. Please, for the sake of our recording, give us a big round of applause for Rich right now. Thank you.
Thank you very much, Warren. I am going to use slides, and if some people on the edges, if you wanted to move there's a few seats sprinkled around. There's a few at the back. You might want to move. And you can do it at any time. No one will mind. I won't mind. Good one. So we're here to celebrate tea time, the end of tea time. Tea time is a wonderful thing. I think it's where we come together. We share ideas. We share half-baked ideas, all kinds of ideas, and our insights, and try to figure out what's important, what's not important. Because I think we are, we're not the whole Alberta AI research community. I mean, we fill the room, but the community really is much, much larger. So maybe we're like the core of the Alberta AI research community. And we might think about that. And the Alberta view of AI is different. I'm sure you've got a sense of that. And I won't try to put a label on it or characterize it, but it is distinctive. And I think we have something to bring. You know, are we like an obscure research community on the edge of the subarctic? Or are we, well, I guess we are an obscure research community on the edge of the subarctic, but still I think we have something to offer. And I think we should embrace our distinctiveness and who we are, and well, while always questioning it. So today, I'm going to share with you my thoughts about planning, my thoughts, and Michael Bowling's thoughts, and Patrick Pilarski's thoughts. And I haven't seen them here. Maybe they've heard me give this talk before. Anyway, they know what I'm going to say. This is really our plan. And there's a document. It's been published in archive, and it's jointly authored. It's our group plan. And so what am I going to say today? Well, I always want to make sure that I get the main points across. So I've done what I sometimes do, which is do them on the first slide, you know? So here are the take-home messages for today. First of all, understanding intelligence is a grand scientific prize that may soon be within reach, and the glory will go to those who are bold enough to try to seize this prize of understanding intelligence. And so the Alberta Plan is a direct run at this prize, and so we emphasize intelligence as the acquisition of new knowledge rather than as something that is static or built and doesn't further learn. Yeah, and my motivation stems from this, my motivation for the architecture, so like the end point of the architecture, what it builds to, I mean, for the plan, is what it builds to. It's actually step 11 of 12, is what I call the oak architecture. So I'll be telling you about that. It's a complete conceptual design for a model-based RL agent or a proto-AI. And the one last general point is that the Alberta Plan is in some sense a massive retreat from the cutting edge of deep reinforcement learning. We're going to go back to the most basic algorithms and revamp them so that they're more suited for continual learning and for meta learning. Okay, so let's get started. The first thing is that we should, reinforcement learning research, generally AI researchers, should keep our eyes on this big prize of understanding the principles of intelligence. what it is and how it works well enough to create or become beings of far greater intelligence than normal current humans. This is a big, big deal, right? We're talking about reproducing the essential abilities that make people intelligent, and being able to recreate that with technology, and that will open up lots of possibilities, and it will change the world, absolutely. It's a step in the evolution of life and intelligence. You know, it's hard to say how big it is. You know, I say here, I think this is good, this is reasonable, that it's comparable to the rise of life on our planet. It's the point when life figures out itself and can make more life, you know, without replication, but through design. This is a big deal. It will change everything. In some sense, it's bigger than our paltry worries like the economy is in trouble or something like that. This is a much bigger step. Okay, now I also want you to, I want to compare it to like some of the great scientific contributions of the past. And not that I'm claiming it, well, it hasn't happened yet. So, but at some point it will happen. And I want to compare it to the contributions of Einstein and Darwin and Newton and Copernicus, Watson, all these people that are famous for making a scientific change that changed the way we view ourselves. And like none of these guys became rich because of their science, okay? None of them like designed an app that helped us, you know? I think we are over-concerned, that's this point. The significance of this scientific prize is not derivative because it's gonna help us, our lives be more comfortable. That's not the source of it being an important thing. So, you know, like what contributions are more like the ones that bring benefits, like Thomas Edison developed the light bulb. I think that helped us all, but it wasn't really a change in our view of the world or of ourselves. Gutenberg invented the printing press. That's a big deal. And similarly, you know, like Page and Brin, they did the Google search engine, which has sort of changed their life, but it wasn't this fundamental scientific thing. Even the invention of computers, which we might attribute to Babbage, is just a technological step. It's, okay, so I'm trying to help you think about how big what we're talking about, understanding ourselves well enough to create them, how big of a step that will be. I think it's a giant step. We can talk about what exactly would it be, but it's a big deal. It's this grand scientific prize. And I want to, without going through this slide, I want to remind you of the reasons why we think it's not being totally arrogant to think that this might happen within the next few decades. So it basically comes from Moore's law, computer power per dollar increasing exponentially with no end per sight. And it creates a powerful, persistent pressure for what we're doing, for trying to understand intelligence. And this is, I estimate like a 1 chance in 4 that we will understand intelligence in a significant level, that we can create AI that's not unlike people by 2030, and shortly after that, it'll be much beyond. Okay, so that's the backdrop as we try to think about this. So we create, the Alberta Plan is a document just published in Archive. It's a 12-step plan, you know, for those of us that need it. It's a roadmap for AI research by Mike and Patrick and myself. And it's not a policy, you know, I call it the Alberta Plan. That's how we brand it. But it's not a policy of Amii. It's not a policy of the university or the province of Alberta. It's the planning process that we all have to do in order to be most productive, to work together, to think about where we're going and where we might want to go to think about it. So generally, if we are clear in our communications, then we can take a more direct path towards understanding intelligence. So the Alberta Plan is based on what you might think of as the standard reinforcement learning picture. An agent interacts with an environment. It generates actions. It perceives some sensory observations, and it has a goal, which we formalize in the form of a reward. So there are a couple more distinctive things that are actually suggested here in the bullet point. This is, the agent is complex, it's intelligent, but the environment is vastly more complex. So this is what we call the big world perspective. A little bit of a conflict of terminology, world and environment. We think the environment is complex and complicated, and it's big, much bigger than the agent. Okay, so because it's much bigger, there's no way we can find the optimal solution. The agent will not find the optimal solution. It will find an approximate solution. And the best approximation will change over time, so the agent will have to track it, the best approximate solution. So I'll come back to this in a bit, but that's the basic perspective. Complex agent interacts with a much more complex environment. And the interaction is continual, just like it is with an animal, just like it is with you and me interacting with our worlds. We don't pause and we don't collect data and then go back and think about it, or at least not primarily. It's continual, it's temporally uniform, there are no special training periods, there are no episodes, and there's no discounting. And finally, actions and observations. These things are just signals. They're just data, they're just information. They don't have any intrinsic meaning. Like nothing comes, well, I guess the exception is reward. Reward has intrinsic meaning that it's good. It's what you're trying to obtain. But all the, all the observations are just hints to when you should do various things, and all the things you might do are just things you could do. They have no intrinsic information. And if we want generality, then there's nothing that's specific to our own way of thinking. Anyway, this is a strict observation of the Alberta Plan. I want to elaborate on this. So the key point is that we're eschewing domain knowledge. The plan should contain, let me first be specific and clear what I'm proposing. The plan should contain, before you agree or disagree with me, what we're thinking is that the plan should contain nothing specific to the human world, to the human environment. Nothing about vision, nothing about space, nothing about objects, nothing about language, nothing about other agents, except of course there will be other agents. But there's nothing in the observations or actions that pertains, is labeled by these things. So there's nothing that distinguishes people from other animals. I wouldn't want that, because I'm really trying to understand intelligence. I'm not trying to understand human intelligence if it's in its specialties, specialness. So nothing about specific ecological niches, no content like, it's good to think of the world in terms of objects, or there are multiple intelligent agents in the world. That's all content. Instead, we are seeking algorithms for acquiring and organizing that content. So, you can summarize all that and say learning first, domain knowledge last. Not that you might not want to put it in, but it's not the topic really. And why? Why to do this? Well, mainly we do this. It's just striking me right now that I've got a gizmo somewhere for advancing the slides. Where did I put it? Ah, there's the gizmo. Good, now I can walk around a little bit. Okay, so we're doing this, eschewing domain knowledge, because we want to keep the problem small. And if it involves the domain is huge, right? The domain is the world is much bigger than the agent. There's lots to know. And so we want the methods to be small and scalable, and we want to keep the focus on the acquisition of knowledge rather than putting in stuff that you might already know. Okay, so generally speaking, the Alberta Plan's research vision, it's all about intelligence as signal processing over time, and we have these key features like, there's a document, I'm not going to go through the whole document, but I want to hit some of the main points and then before going into the steps, the 12 steps. So the main sort of scientific orientations or commitments in the Alberta Plan is that we're focusing on experience. Experience is the data of AI. We want it to be online, temporally uniform, continually running, like me. And we are going to respect computational costs. Those are important. They're not negligible. And the agents are interacting within the environments that are containing other agents. Okay, so what can I already said, you've seen the big picture, the agent interacting with the world. That's really important. The next step is to look inside the agent a little bit. So in proceeding to this step, a good place to start is with what I call the common model of the intelligent agent. It's common to all of these fields. It's common to many fields, common to AI, of course, and but also psychology, and also economics, also control theory and neuroscience, operations research. These all have, if you look at them and try to understand, at a distance what's going on in those fields, they have certain common ideas, and it comes because they're looking at the same kind of problem. They're all looking at decision making over time to achieve a goal. So it's a good place to think, what are the common elements that all these fields have in common when they're talking about the internals of the decision making agent? Okay, so I identify this picture of the agent, and I guess I can point here. There are four main, this is just the inside of that agent box we saw before, and then there are four boxes inside, and they're connected by a state representation of where you are. So the box that produces the state representation is perception. Sometimes in this group we call it the agent's state update function. Okay, but it's really perception. It's how you turn the data stream into a sense of where you are, what state you're in. Okay, so that's the first step. And then that continues straight through to the policy. We make decisions, and we have to make the decisions based on the state. The state also goes to the value function. The value function evaluates the decisions that are made and basically says how well are things going. The value function has to have access to the reward and the state, and it produces, well, I want you to think about that green line being produced there. That's the TD error, and it is responsible for learning in the policy. Okay, so those are make up model-free reinforcement learning. And then the fourth box is the transition model, is the model of the world. And that's responsible for planning, and planning should also change the policy. And it also changes the value function, but it made the diagram a little too complex to try to draw that in. Okay, so these four elements are they're very familiar to us from reinforcement learning, but they are also present in other fields. In control theory, they will have control laws, and they will have objective functions, and they will have a system model. They will have a state estimator, right? They have all these things. In psychology, we have perception, we have stimulus response mappings, we have models of the world, we have emotions that correspond to the values of the states as we go through them. So all these fields really have these things, and we shouldn't consider this to be exclusively our field's view. Okay, maybe we've crystallized it a little bit. Now, this is what I've identified and written about as a model of the intelligent agent that's common to many fields. But in the Alberta Plan, we're going to use a slight elaboration of this. Okay, so this is the elaboration. If you look at it really carefully, the only thing that's changed is inside those lower two boxes. This is now plural. There are multiple value functions and multiple policies. Okay, otherwise it's the same. Somewhat behind the scenes, so it makes any cartoon, any diagram like this, box diagram like this, is ultimately a cartoon, and you have to stretch it. But the additional thing is there are subtasks. So the idea is that the agent, in addition to figuring out what to do and how good it is, and maybe modeling the world, it should also work on other subtasks, like how do you walk, or how do you open a door, or how do you drive to Startup Edmonton. I guess that won't be useful anymore now that they're taking it down. But so these are all subtasks, and in the Alberta Plan, they are much like feature control subtasks that you may have read about in the literature, where you have some feature and then the subtask is to turn that feature on or off. These are feature-based subtasks, and they give you multiple policies and multiple value functions. And then, now I'm ready to say about the endpoint, the oak architecture. The oak architecture is, oak, it's just a fun word. Maybe it stands for options and knowledge. It is the proposed architecture that we're working toward in the Alberta Plan. And it has these elements with the subtasks. And, so I don't want to give all the, I can't say everything today, but I can give you just the briefest overview of what the oak architecture is like. The oak architecture, by the way, is not written up. There is no archive document on the oak architecture. There's a few talks. So what you're going to hear today, you really can't get elsewhere. The key idea is a cycle of discovery, because we not only want to learn the things, we want to also discover the abstractions. That's like the step after, I can learn the policy, I can learn a value function, I can learn a model, what will happen next if I do this action. But really, these all have to be done in a more abstract way. Like the model, you have to say, I could go to Edmonton. I can go to Startup Edmonton. It's not one action, it's a policy, it's a way of behaving. That's what an option is meant to be. An option is a way of behaving that terminates, and it's your abstraction for action. The abstraction for state is a state feature. So we're also concerned with how you find the right state representations. Many of us are concerned with that. And so the oak architecture is a design for answering that question. And at its core is a cycle of discovery. Discovery means we're discovering the abstractions. And so let me try to show you how that cycle works. It starts with the features of the state representation. Right? Think of the state representation as a feature vector. Okay, so you have 10,000 features characterizing where you are now. And so we have these state features, and then we can rank our state features by how important they seem to be, and then we can take the top subset of the features and turn them into subtasks. So the idea is that once you have identified a feature, that automatically defines a subtask. The subtask is to achieve that feature while not losing too much reward. Okay, so the specifics, that's the general idea. A feature defines a subtask to attain that feature. And then the option is the policy and the value function for attaining that feature. So I'm just distinguishing the task and the solution. The task is to attain the feature. The solution is the option, which behaves in a way and succeeds, hopefully, in attaining the feature. And the value function is the value function you use to find that policy. So these are two definitional steps, right? I haven't had to learn anything. So I can rank my features and find some good features. It defines a set of subtasks. And then once I have those subtasks, that defines, in a sense, their solutions. It doesn't enable me to find their solutions, but it does define them. And then with experience, you can find them. Okay, so we bring in experience, and now we can do it. And in order to find those solutions, you will use the state features. You'll say, if this state feature is true, then I'll do this action. If the state feature is not true, I'll do another action. So you actually have to use the state features. This is a different sense. It's not definitional. It's I'm learning this function, the policy function and the value function, and the inputs to those functions are features. Okay, the features of the state in particular. Okay, so notice the arrows show the direction of the primary flow of information. Okay, but there's a backwards flow. There's a slower backwards flow, because the backwards flow is how you do credit. You say, like each guy's whose arrow is into him, like this one, these options values, they use some of the features and they don't use some of the features. And so if I use if the options use a feature, that shows that the feature is useful. Okay, and so it provides feedback to the feature construction process to say, that was a good feature. Please don't change it out from under me. Okay, don't change very much. So this is a backwards flow. It's very important. I mentioned we rank the features, so we're going to rank them based on their usefulness to the rest of the system. Okay, next cycle part. once we have a way of behaving, we can ask, well, if I behave that way, where will I end up? Right? And that's the model of the option. Where will I end up because the option, I've said it a couple times, but the option is literally a policy and a way of terminating that policy. So once you have the option, you can run it, you can see where it ends up. And that provides the training information to learn the model. And notice this is not a low-level model. This is a high-level model. One of the options, maybe a feature is, I want to get to, maybe I have a feature for being in Startup Edmonton, okay? And then I'd have a way of, I would learn how to get there, or maybe I would consult a map. Anyway, I end up with a policy for getting there, and it terminates when I get here, and then I can figure out if the policy I have is reliable, whether it actually gets me to Edmonton, to Startup Edmonton, or doesn't. And by the way, the model also has to tell you like how expensive, how much it will cost you, how much reward you will get or fail to get because you're going to Startup Edmonton rather than to the Amii building or something else, or staying at home. So that's the model is, and that is another definitional step. So once you have the way of behaving, it defines the correct solution to the model. Okay? Doesn't mean you know the correct solution, but it defines it. And then again, you have to take experience and you have to use the state features in order to form that model. And okay, you guys got the picture? Okay, now this again provides more feedback back to the state features. Now, why are we making this model? We're making the model so we can plan. What does planning mean? Planning means using the model, a computational process using the model, and not necessarily any more experience to improve the policies. And that would be both the main policy, the reactive policy, and also all these policies listed here, the policies that are inside the options. Okay, so let's now just consider both of those things in that box. And the main policy is just the policy that says, I'm not trying to get anywhere, but I just want to get a lot of reward. And so really then this cycle encapsulates all the policies are there in that area. And that's the cycle of discovery. As I said, the consumers of the abstractions, consumers of the state features, evaluate the state features. The consumers of the options, which is the model, and ultimately the planning process uses the models. And it will find some options, models of some options useful, others, models of other options will not be useful. And this provides feedback to the option constructor to say, oh, that was a good option. And the feedback I'm talking about is just, I'm using your option, so don't mess it up. I'm not providing all that detailed feedback, but it is real feedback. And it says, preserve these things that are found to be useful and rank them highly. So we will, this is what makes it a full cycle, because we are now ranking, we're going to re-rank the features, we're going to re-rank the options, and this will now generate new subtasks, because the different features will now be most important, and the cycle continues. Okay, so this is the broad outlines of how we expect to form the abstractions that are maybe all that's needed for the next big step in AI. And just notice that all of it is ultimately tied to reward and tailored to the environment. The abstractions are ultimately tied to that. Okay. Any quick questions? I'm going to go on now. Okay. That's the picture for what we're doing today. And my motivation is I want to end up at this oak architecture. And the Alberta Plan, as I said, is master retreat. And let's go to the 12 steps of the Alberta Plan. Okay, here I'm listing them all. I'm not going to go through all of them. Actually, I'm going to go through some of them, though. And they all make sense, I think, in terms of this diagram. All the representation things are about finding the state representation. Prediction is what the value function does. Prediction is what the transition model does. Control is what the policies do. And prototypes, AIs, are where we try to bring it all together. Planning is where we use the model to improve the policies. also part of control then. Maybe I'll mention step 10 while it's up here. It's the stomp progression. The stomp progression is like 3/4 of oak, and stomp has a paper. Right? You can find, I guess it hasn't been accepted anywhere yet, but it's on archive for the stomp progression. It's called reward respecting subtasks, because these subtasks are reward respecting. The subtask is to achieve this feature while getting good reward. So it's not divorced from reward. Reward respecting subtasks is the key word if you want to get that paper. Stomp paper. Okay, so now I'm going to go through the first 6 steps, and then we'll be done, because in a sense I've done 9, 10, 11, all those other ones. I've sort of done them. You've seen where we're going to end up. But the first 6 steps are really where we start. They're not first for no reason. We want to do them first. Okay? But before that, I have to go through the big world perspective in a little more detail. I'd like to go through it in a little more detail, because they are the motivation. That's the motivation. So the world, so this is what we mentioned before. The world is vastly more complex than the agent. After all, the world contains many other agents, and what is going on in their minds matters to your mind. If you say something, you offend someone, or you introduce an idea to them, it influences your behavior. So you actually are fully, genuinely concerned with what's happening in other people's minds. Okay, so it follows, because there are so many, your mind is complex, their mind is equally complex, and there are many of them. You are much less complex than the environment, than the world. You can never accurately know the state of the world, what's going on in other people's minds, what's going on in other galaxies. You can't know the state even of a glass of water. So what you do have is some gross approximation, some simplified model. I have the model that there's a glass or a plastic cup there. That's a simplification. There's really much more detail. So, I think this alone makes the idea of prior knowledge a never-ending fool's errand. You can never get everything about reality. And the facts that you're going to know, you growing up in Edmonton, is different than if you grew up in Africa. Your life is always, the knowledge you need to have is specific to where you are, and it's specific to your body and the way it's been constructed up individually. But there's too much to know, and it'll depend on your life. You have to adapt to the particular part. And you have to do this continually as you encounter different parts, as you may learn to walk, and then you may sprain your ankle or have other problems, and you have to walk a different way. Your approximations are going to be non-stationary, and they have to track. And this is what we mean by continual learning. Continual learning, you may have heard, it's becoming a buzzword. It just means that you keep learning. Like, I want to say, duh. Of course, you would learn. If you stopped learning, you wouldn't even be a learning system. You'd be a learned system. But anyway, continual learning is becoming the buzzword for actually recognizing the importance of this. And once you are in a continual learning setting, then you get repetitive experience with learning. You learned one way and it was worked out, generalized well, learned another way, didn't work out as well. So you get this sort of meta experience, and you can learn how to learn better, okay? It comes immediately out of the continual learning perspective. Leads you immediately into learning to learn, which is called meta learning. Meta learning is the other buzzword. And so these are the two things that really is the seed for the Alberta Plan. Okay, so it's this implication. The big world perspective leads directly to continual learning and meta learning. Meta learning, the favorite example is representation learning. These things are naturally linked. Okay, so now step 1, not all the steps are going to be gone through with this much detail, but step 1, it is a good example of the whole plan, because it's a retreat. And we retreat far enough where we can study each issue in isolation in a simple setting, the simplest setting in which it arises, ideally. Okay, so in step one, the issue we want to focus on is continual learning and meta learning, right? Maybe that's two issues, maybe it's one. Anyway, we want to focus on these things in the simplest possible setting. And the simplest possible setting, perhaps, is linear supervised learning with a fixed set of features. There's no fancy deep learning. We just have some features, and we have to stick with those, but we want to use them as best we can. Maybe we want to learn which ones are most important. Okay? It's linear supervised learning. And we've been doing this one for a while. The first thing that comes up is normalizing the features. The features could be scaled in very different ways, and that has a powerful effect, and you want to control for that. So if you normalize them, which means like translating, shifting them, and like an offset, and scaling their variance, this is an important first step. And doing this has been studied, but not so much in the online setting. Like it's done all the time in deep learning. It's called batch normalization. Well, this would be online normalization. This has not been refined. It's not been. We want to perfect these things. We want to do as well as we can on these simple things, because it's just going to get more complicated. Okay. So, and then so that's really the meta learning part, and the continual learning part. And the meta learning part is learning feature relevance. So you have this set of features. You can't change them, but you can learn which ones are more important and more relevant. In fact, what it literally means is the step size for each feature. And so we want to fully understand that. And as many of you know, there are methods for doing that, such as IDBD or IDBID, which have done some work in that direction, but it's by no means finished. It's sort of begun. It's not finished. For example, IDBID is a way of doing gradient descent at the meta level, and it finds eventually the right step sizes, but it doesn't find them efficiently. It doesn't find them fast. To use such methods, you need to find them efficiently. And so that's what step one is all about, normalizing and finding step sizes, and this is being pursued now by Thomas Degree in DeepMind, and Khurram Javed, who's just over there from the university, and by some other folks. And maybe we're about half done. I think we can see the end at this point. Okay, step two. Step two, we don't just accept the features, we try to find better features. Okay, so we're going to add new features that are nonlinear functions of existing features, as in regular deep learning. But we're going to do this in a way that retains everything we obtained in step one. We're going to retain the ability to have normalization and continual learning and meta learning with adjusting our step sizes. So we're still going to be doing stochastic gradient descent, backprop, but it's going to be different with per weight online normalization and step size adaptation. And in addition, we need an element of random creation. And random creation as in, like let's make some random features and evaluate them. Let's not always crawl along gradients. And let me just mention the thing at the very bottom there. This is work that was pioneered by Rupam, who was also in the audience, Rupam Mahmood, in his PhD thesis. And right now, Shubhansh Dohar, Fernando Hernandez Garcia, Parash Raman, and Rupam and myself are writing a paper also that's directly relevant to this. Okay, but then the last bullet is that this step, if it's pursued successfully, I believe will produce a new form of deep learning that designed from the beginning for continual learning and meta learning, and that will revolutionize deep learning. Doesn't mean it's going to come from here, but this I think will end up having that effect. Anyway, that's the intention behind its role in the plan. Step three is now for the first time we're going to do something that isn't IID, that isn't pure supervised learning with all the examples can be shuffled in any order. Now we have a temporal element. We're doing genuine prediction. We have a sequence of data. They have Markov state dependency. It would now make sense to use something happens earlier to try to predict something will happen later. So we're getting closer to reinforcement learning, but we're not having control. We're having prediction, but not control. So the natural setting here is off-policy learning general value functions that many of you know about, or GVFs, we often call them. But we want to have the learning processes. Now for them, which we have learning processes that can do okay, off-policy learning GVFs, but they don't work in multi-layer networks with continual learning, and they don't do meta learning, and they don't do step size adaptation. So we want to do all the things that we can do now crudely and non-robustly, and without the meta learning in ways that don't work well in continual. We want to do them all in this more effective way, for more way that's more suited to our goals. So we're going to need several new elements having to do with the eligibility traces and the delays and the errors. But the biggest challenge, I think, will be once you have a state dependency, a genuine sequential problem, you have to find the state representation. So you have to find the memories. You have a real, genuine state problem. You have to know what of the old input to remember in order to make you good predictions in the future. So this is the state part. And so we can study the state part in a prediction setting before we go on to the next step, which obviously will be to do control, a genuine reinforcement learning setting, which again carries the novelties from continual learning and meta learning, step size adaptation along. And we'll do it first totally model free, and we'll probably will be episodic actor critic. There will be some new challenges, setting the two kinds of step sizes that involve an actor critic to get good continual learning of non-stationary approximations will be a new challenge. And it's new in the sense of it doesn't arise until we get to step 4. And step 5 will be average reward. I won't say much about this, but this is where we get rid of discounting and we switch to differential value functions. Some work has been done on this, but it hasn't been fully integrated with all the imagined things for the earlier steps. Okay, and the last of the 6 steps, and these are the last of the model-free refinement steps, reinforcement learning steps, is to go to continuing control problems. So remember, you may not have noticed, but the easy case in continuing control was episodic, so you don't have to worry about average reward or anything like that. Now when you go to the real case, continuing, time goes on and on, it's not broken up into episodes that end, then that's the continuing control case. Okay, and part of this will be developing C-suite. Abhishek is working on that part with some folks here and there. So with step 6, we'll have revamped all our essential model-free elements, and if they're well done, I think it will be a revolution in our ability of our model-free methods, and they'll be much more robust, and they'll be involving the discovery of abstractions, and all these things are essential for preparing us for the next steps, which are working towards model-based reinforcement learning. Okay, so I'm kind of done. I'm not going to go further into the steps. The first steps, revamp. I want to mention that they're revamping model-free reinforcement learning, but they're also revamp our ability to learn the transition model. So it's really all 4 of the steps that are fundamentally changed if you get the first 6 steps done. And the steps 9 through 11, or maybe even 7 through 11, which are about planning and about integration, we've already talked about them when we talked about OAK. So we really have covered everything except for step 12, okay? So let me just, on my last slide, or almost the last slide, let me do step 12. Step 12 is prototype IA. IA is intelligence amplification, sort of the opposite of AI. It's not really the opposite, it's the other half of it. We want to create things that are new and intelligent, but we also want to amplify human intelligence. And so this part, it's about what Patrick is doing now to integrate machines and people working together as an intelligent prostheses. Many of you know about that, but it's not just that. It's in part, it's about just machines and people working together more generally. Okay, so this integration could be very tight, us and the machines. You might end up being what you think of as another lobe of your brain. I know many of you think that, like, you know, Google search is already another lobe of your brain. Certainly you rely on it for many, many things. But we carry this, why won't this just be carried much further into an extreme? You'll have machines tightly integrated with your brain, or richer sense organs that you could integrate into your brain, and actuators. Or the integration could be looser than that, right? This classic looser integration is you have an assistant that helps you, and they're automated, and they help you run your calendar and your mail and your life. Or we can make it still looser, in which you would have, like I call free AIs. AIs that are not dedicated to you and helping you run your life, but they are intelligent agents like yourself. And this is where, and we would work together with them, just as we work together with each other. And so if the free AIs taking their proper full place in our society and our economy. So this is where, you know, this slide here is really going beyond the Alberta Plan, but, you know, we have to situate everything in the ultimate goals. And the ultimate goals for me is we want to think a bit about AIs and the role they play in our society. And we want it to be done well. We want it to come out well. And so I'm very optimistic that we can work well with our machines to everyone's benefit. But we all should take responsibility for this working out well, and we should play a part in it, play a part in making the positive outcome likely and widespread. Okay, so this is a good place to stop. Let me just remind you my take-home messages for the plan itself. Understanding intelligence, see as a grand scientific prize that may soon be within reach. The glory will go to those who go running after it, and actually only those who succeed at it. So we're trying to succeed at it. That's what the Alberta Plan is about. Motivation for the plan stems from the oak architecture as the final endpoint, possible endpoint. The Alberta Plan is a master retreat in the sense of going back to the basics. And remember, all plans, you know, will fall apart in contact with reality, and we'll have to change this as we go along. So I welcome working with you guys to evaluate the steps and proceed on the steps and revising the steps as needed. Thank you very much for your attention.
Awesome. Thank you. So we have time for a few questions, but we're going to have to pass the mic around. So we'll take a minute if someone has something right off the bat they want to ask Rich. All right. Help me out and pass that to the gentleman at the back.
Yeah, thank you, Rich, for a wonderful talk. So this is a very basic question, right? Maybe primitive, maybe not even a question. It's about what you started with, the agent model, right? The agent environment model of vision, reward, and action. You call those signals, right? And one thing I wonder about is actually the time relationship at that level. Because later in your talk, you actually devoted a lot of discussion to how to deal with time, right? Delayed reward and so on and so forth. So, but do you have similar issues over there?
In the model?
So, yes, the model itself at the action reward opposition level, whether there are timing issues there, essentially. Yeah.
Yeah,
Okay.
so let me be explicit about that. The model of the world has to be temporally non-trivial. It has to be temporally abstract. Like the obvious thing, and let me just say it so we can say that's not what I'm talking about. The obvious thing is to think about a physics engine that can, at a low level, model the world and propagate steps forward at some micro level. If you make a model of a Markov decision process, that's also at the lowest possible level. But our understanding of the world is not at the lowest possible level. It's at higher levels. So when I'm using the example of I can learn a policy or a model step, like if I behave this way, I will end up at start of Edmonton. Or if I behave in this way, I will find the restroom, okay? Or if I behave in this way, I can have the cup in my hand and I can be drinking sweet water from it. So none of those are physics models. Those are life models. Those are the decisions that you actually use to make up your life. So think about, it's summer now, maybe you're thinking about going on vacation. You know, you can go to this place or to that place. Those are the real decisions you're making. You could decide to take this airplane or that airplane. These are not physics models. These are not low-level models. So they are examples that we can easily relate to that show that our understanding of the world is not at a micro level. And so the world model is absolutely not got to be, is absolutely not at the micro level. Thank you for the question. Mohammed.
Yeah. Hi, Rich. So with your oak architecture, like there was a mention, well, cycle was an essential part of it, the word cycle. I was wondering if your cycle is closed in that part of the diagram you showed, or is being closed, it's being a cycle from something that is not shown in the model, in your diagram.
Thanks for giving me a chance to clarify that. You're right. If you think, look just at the arrows. Whoa. Somehow I missed it. If you look just at the arrows, it doesn't look like a cycle. Here it is. Because it, here, that should complete the circle, but it's not in a cyclic form. It's coming out from the features. So in order to, the cycle though is completed because of the backward flow of information along, say, the green arrows, which inform the features whether they're useful or not. So while using them in the forward direction, here, you also send information back on the utility of the features. And that's also happening along this green arrow. And that is how the cycle is completed. Now, there's also here, because when you use the models of the options for planning, that also provides feedback. Principally, planning is you're saying, well, what if I do this, or what if I do that? And you think, oh, the model tells you, oh, well, that would work out this way, and then you say, oh, that would be good. Okay, but you may think, I could walk to the start of Edmonton, or I could take the subway, or I could, I don't know, twiddle my thumbs, or I could play Monopoly, or I could, do a zillion other things. And so planning is full of that. There's all these things you can do, and if you just have a zillion other things and you have a huge branching factor, and planning is not effective. So whenever you're doing planning, you're going to think about different possibilities. Some of them will say, oh yeah, that'll be good. Most of them will say, no, that's stupid. Okay? But when you say it's good, that is feedback to the suggester of options in planning. So as you plan, you're always finding information about what it's useful to think about and what is not useful to think about. So I have an option, maybe it successfully achieves some feature, but that option is never useful in planning, or the model of the option is never useful in planning. That is feedback to that option that I I don't use it in planning. I shouldn't use it at all. I could reclaim my resources that were devoted to achieving that options and use them for achieve some other feature. Okay, so in these ways, there's a genuine substantive closure to the loop, the cycle. Thank you, Mohammed.
Thanks. So one quick question, like, so do you think like the models of the world should be reward respecting as well, like, you know, the subclasses?
Yes, yes.
That's great.
Yeah.
So another thing is that, so you talked about meta learning, right? And like learning to learn.
Yes.
And continual learning was like one of the two major parts of the
Yes.
like first step. So I was wondering, like, you know, we are always talking about learning to learn, but like, why just this one step? Why not like learn to learn to learn? Because when you kind of go for meta learning, you also come up with new hyperparameters, and they are also going to be sensitive.
Yes.
So why do you
Indeed.
think like just that step is enough?
I think indeed, yes. One step at a time, but we will want to do meta and meta. You ever hear that old saying, you know, anything you can do, I can do meta? Anything you can learn, I can learn meta.
So my last question is that you talked about the connection of, you know, the whole architecture that you kind of proposed with like economy, psychology, and all those other stuff.
Yeah.
Do you think that there are just shared components between reinforcement learning and those kind of sub areas, or is there also, you know, they have a common goal as well?
Yeah. Yeah. What they have in common is they're all about decision making over time to achieve a goal.
Yeah.
Yeah. And that I think is the source of their common structure in their solutions.
Yeah, I totally get that about like economy, because it's kind of managing a scarce resources for well-being of society. If you just, you know,
No,
take
it's
it down.
not because of that. It's because economics, a significant portion of it is about modeling the decision makers, modeling the people and what they're doing. It's not the part that tries to think about how resources are optimized in the economy. It's the modeling of the individual people. That is also done. It's not the only thing that's done in economics, but it's one of the main things. So you can find in economics rewards and value functions, and maybe those are the main things that are common in economics.
I see. Thanks.
One more non-horrifying question, if it's out there. It's out there. All right.
Hi. So there are some physicists like Roger Penrose who argue that quantum mechanics might play a role in intelligent decision making. In fact, there are like fields coming up such as quantum biology, which also argue about the same thing. So what are your thoughts about that? Do you think quantum mechanics might have some role in intelligent decision making in humans or any other animals?
Well, I don't want to be too flip, but no, I don't think we need any special physics in order to do AI. I think it's all classical mechanisms classical physics will be sufficient to do all of intelligence.
Thank you.
Thank you.
Awesome. I know there's going to be some spicy conversation after this, so I'm excited about that. We're going to give another big round of applause for an awesome and inspiring talk from Rich. Thank you so much.